In this video, we're going to evaluate an integral using the definition of the definite integral and left or right endpoint approximations. It says use the definition of the definite integral to evaluate the following integral. Use a right endpoint approximation to generate the Riemann sum. So they give us the integral from 3 to 10, and that's of x squared plus 2 dx. So the first thing I want to do is I want to write out that what my area is going to equal based on previous sections when we did our approximating with lower and upper sums, and we did left and right endpoint approximations. So we're going to say that A is equal to f of x1. So this is for the right endpoint. We start at x1 when we're doing the right one, and we start at x is 0 when we're doing the left one. So f of x1 times change of x plus f of x2 times change of x plus, I'm just going to write plus dot 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 plus, we end up with f of xn change of x. So that's how we found the areas in our previous section. What this would always equal then, so we would say that this is equal to we have a Riemann sum, which would be the sum from I equals 1 to n of f of xi. And we can say f of xi because I is 1, so that starts us at x1 just like we have here, times change of x. Now if we applied this to the definite integral, all the definite integral does is it states that if you have an integration from a to b of some function f of x dx, that is equal to basically this formula with the limit as n approaches infinity for this n value. So we sum I equal 1 to n f of xi change of x. So we take the limit from n to infinity. So this just continues to sum forever and ever and ever till we get basically our exact answer. That's how that works for this integration. So what we want to do to start this problem off is we want to say, what is change of x? We want to find change of x, we want to find xi, and we want to find f of xi. Once we get all that stuff, we can actually do the Riemann sum. So let's start by finding change of x. So I'm going to write up here change of x is equal to b minus a over n, which this is a and this is b. A is my lower bound, b is my upper bound. So I have 10 minus 3 over n, which is 7 over n for change of x. What is xi? Well, xi is going to equal, and we get this from our previous section, xi is equal to x sub 0, and we add I change of x. Now I want to talk about this just a second. We always, in our previous section, we would always add change of x to x sub 0 because that would give us our widths for our rectangles. So we say x sub I because I is going to start at 1 here. We're going to say x sub 1. And we would want to take 1 times change of x. But when it's x sub 2, we actually take 2 times the width to get the new x value. So this expression represents basically our sections for our rectangles being cut up. We can start to substitute some stuff into that. So x sub 0 is this 3 spot, a. So we're going to say 3 plus I, and then change of x we just found was 7 over n, written right here. So we can write that as equal to 3 plus 7i over n which is 3n over n when I find a common denominator, plus 7i over n, which gives you 3n plus 7i over n. Or we can reverse that and write that as 7i plus 3n over n. So now that we have xi, we want to find what f of xi is. Well, f of xi is going to be our function, which is x squared plus 2, with xi substituted in there. So we're going to say that this is 7i plus 3n over n squared plus 2. And then what I'm going to do is I'm going to square this piece in there. So we're going to get, we're just going to write this as 7i plus 3n squared over n squared plus 2. And now I'm going to write this whole Riemann sum out, which is right here. And I'm going to start to evaluate it. And it's going to take a second. There's some algebra that is involved here. A lot of it. So limit as n approaches infinity of the summation I equal 1 to n for f of xi. Well, I just found f of xi to be this. So that's 7i plus 3n squared divided by n squared plus 2 times change of x, which is 7 over n. So I'm going to go through and I'm going to start to simplify this whole thing. And to simplify this thing, we're going to distribute 7 over n to each term. So we're going to just write that this is equal to, and I'm going to leave the limit here. Remember the limits on this at the end, but I'm going to just kind of like do all this algebra and then rewrite it at the end. So we have the summation from I equal 1 to n. If we distribute 7 over n, we get 7i plus 3n squared over n cubed plus 14 over n. And then we can, let's see, I think we should square this piece and see what we end up with. So let's go ahead and square this piece on top. So we'll end up with equals the summation I equal 1 to n. If I square the top, I get 7 times, this will be 49i squared plus 3n times 7i, that'll be 21i n plus 21i n plus, when I square this 3n, I end up with 9n squared all over n cubed plus 14 over n. Now I think I'm going to let's find a common denominator here. So we're going to basically multiply this by n squared over n squared. And then I'm going to combine that with this top while I'm distributing the 7. So if I take 7 times 49, I get 343. So I have the summation from I equal 1 to n. This would be 343 I squared plus 7 times 21. Actually, 7 times 42, because 21 plus 21 there is going to be 42. So 42 times 7 is 294. So 294 in plus 63. 7 times 9 plus 63 n squared. And then we'd have plus another 14 n squared here. And that's all over n cubed. Now I'm going to simplify that a little bit. So I'm going to say that's the summation from I equal 1 to n. We're going to say that this is (343) I squared. And I'm going to split the denominator, so that's over n cubed, plus, this will be 294, the n's will cancel, so I get 294 I over n squared when I simplify the n's here. Combine these together, that's really 77 n squared, so I get plus 77, when I simplify here, I get 77 over n. Because the n squareds cancel with the n cubed, and I just get one n left in the bottom. And then I'm going to split my summations between each of these. So I'm going to write this as the sum from I equal 1 to n of 343 I squared over n cubed, plus the sum of I equal 1 to n of 294 I over n squared, plus the sum from I equals 1 to n of 77 over n. And then I'm going to factor some things out. So I'm going to write this as, all this is going to be equal. Let's factor out everything except for I squared. And the reason I'm going to do that, I'll show you in just a second. So factor out 343 over n cubed. And we have the summation from I equal 1 to n of I squared, plus the summation, plus 294 over n squared, and then the summation from I equal 1 to n of I, and then plus factor out 77 over n, and we get the summation from I equal 1 to n of 1. Now the reason we did that is because we're going to be able to use some formulas here. So if you remember from our previous section, we have three formulas here. We have the sum from I equals n of I squared is equal to n plus 1, 2n plus 1 divided by 6. The sum from I equal 1 to n for I is n plus 1 over 2. And then the sum for I equal 1 to n of 1 is n. So we're going to substitute those into this equation. So this is going to equal, if I do this substitution for the I squared, I get 343 over n cubed. And this is multiplied times n plus 1, 2n plus 1 over 6 plus 294 over n squared times n plus 1 over 2 plus 77 over n times just n. Okay, now we can really get going on this. And remember, we still have this limit written out front, and we need to keep that in mind, this limit as n approaches infinity, because that's going to be our ending piece. So what do we do next? So the next piece we're going to do is we're going to basically distribute all this and simplify. And we got a lot of simplifying to do. So let's multiply. This will be 343 over n cubed. And then it's times, let's distribute here, so we get n times 2n. So we're going to get n, parentheses, this would be 2n squared plus n, when I take n times 1. And then 1 times 2n, so plus 2n. And then 1 times 1 would be plus 1. All over 6 still. And then I get n, distribute here, so I get plus, this will be 294 times n squared plus n over 2n squared. And then here I'll just, the n's will cancel, so I get plus 77. So this is going to equal, distribute this n throughout, this will be 3n by the way, so you end up with 343 times 2n cubed plus, this is 3n times n, so that's plus 3n squared. N times 1 would be plus n, all over 6n cubed. Plus, we can rewrite this. This will be 294 n squared over 2n squared. So I'm distributing the 294 to the first term, and I'm splitting the denominator, plus 294 times n over, so this is 294 n over 2n squared, plus 77. Okay, then we're going to get distribute. We're going to do the same thing with these terms. So we're going to distribute these pieces. So 343 times 2, 686. So we're going to get 686 n cubed over 6n cubed when I split that denominator, plus 343 times 3, 1029 n squared over 6n cubed plus 343 n over 6n cubed. We can do some simplifying here on these last two pieces. So 294 divided by 2, 147. The n squareds cancel. And then we get, this would be plus 147 over n plus 77. Okay, let's simplify some more. And we get 686 divided by 6. 686 divided by 3. 686 divided by 2. Okay, we can get this to be 343 over 3 plus 1029 divided by 6. Doesn't work out good. 1029 divided by 3. Okay, so we can divide this by 3. So this would actually be 343 over 2 n plus 343 over 6. I think 343. Yeah, that's not going to work. We're just going to leave it as 343 over 6. 343 over 6n squared. We can combine the 147 to the 77 together. So we get plus 147 over n plus 147 plus 77 is 224. let's combine we can combine, if I multiply this by 2 over 2, I can combine it with this term here, and I'm going to combine 343 over 3 with 224. So I get 1015 over 3. I'm going to multiply this fraction by 2 over 2, so 147. So we get 294 over 2n. So this would be 294 over 2n plus 343. So it's 294 plus 343. 637. So I get plus 637 over 2n. So we've taken care of this term, this term. We got these two terms taken care of. So we have plus 343 over 6n squared. Okay, now remember we were supposed to rewrite this limit as n approaches infinity the whole time. So we need to take the limit, and let's ignore that equal sign for a second, as n approaches infinity for this function here. When we do that, we put a infinity in for n on both of those, and we have a small number divided by a really large number, small number divided by a really large number. Basically, we have 1 over infinity for each of those. We know the limit as n approaches infinity for 1 over n would equal 0. So both of these become 0, so our area for the original integral was 1015 over 3.